Okay, so it's a pleasure to introduce the next presentation of the Congress. Ivan, what? Estaba grabando. Okay, so it's going to be Ivan Pan. It's going to talk about the isotropy of simple polynomial derivations. So it's welcome.
Thank you very much. I would like to thank the organizers for the invitation. It's a great pleasure to be here and be part of this homage a Fernando, a good friend. And then, well, let us start. I will work over an algebraically closed field of characteristic 0 and let AGN, the automorphic group of the K-algebra of polynomials. That is, there is a group with collinear automorphism of the polynomial ring. Then it is an affine invariety. That is AGN is the limit of algebraic varieties where Vk is contained in Vk plus 1 as a closed immersion of affine varieties because it's not an algebraic group. In fact, it's, as one say, an infinite dimension algebraic group for this property. And then it is endowed with the inductive topology that is a subset F, say, is closed if the intersection of F with every Vk is closed. Okay? And then a subgroup of the automorphic group is said to be algebraic if it is an algebraic group in the classical sense, such that the natural action on the space, affine space, is a morphinous algebraic variety. Let me explain a little that because I will do a slight abuse of notation. This is an automorphism of polynomials. And then phi xi is a polynomial. And we may define another map by using these polynomials. Okay? And then I will identify phi and phi tilde. Okay? Then this automorphic act on the affine plane and the affine space, excuse me, as a morphing of algebraic variety. Then one says that G is an algebraic, one algebraic group. We consider also the Kx1xn module of derivations, that is K derivations. An element there is a collinear map which satisfies the Leibniz rule. Okay? And then, naturally, we may act AGN on the derivations by conjugations. Okay? If you conjugate a derivation by an automorphism, like here, automorphism of this polynomial ring, this is once again a derivation. Okay? And then we have this action. And we will denote 8 out D, the isotropy of this action. That is, this is a subgroup of polynomial automorphism, the group of polynomial automorphism that commute with D. Okay? The conjugation class of this subgroup is, in fact, an invariant, naturally. Then we may set a general problem, which is the following: classify derivations for which the isotropy, or the automorphism of the derivation, as one says also, is algebraic in the sense before. Okay? This is complicated in general, very difficult, in fact, because little is known about general derivations. Okay? But the problem is very natural, because one asks for derivations where the symmetry group is controlled, is a variety. Okay? The isotropy is a variety, it's an algebraic group. But there are interesting classes of derivations related to different problems in mathematics, and for example, the simple ones. A derivation is said to be simple if it admits no invariant ideals. For example, the geometric meaning of that, for example, in K equals C, a complex number, then the derivation may be think of a vector field in Cn. The foliation associated to this vector field has no invariant subvarieties. Okay? This is the significance of being simple. Okay. There is also an algebraic meaning, which is interesting, I think. That is the following: the differential Ore extension associated with D is a simple ring. Let me explain that, because it's interesting to observe. If you have, more generally, a ring and a derivation, the idea of Ore was introduced at showing here an indeterminate and consider a polynomial algebra, but which is not commutative, and where the commutator of an element in the algebra is the derivation. And then the structure, the non-commutative structure of this new ring, is measured by the derivation, by the operation of the derivation in the algebra. Then, in this sense, the simplicity may be understood as this property, this ring, is simple in the classical sense, that is, there is no invariant bilateral ideals of this algebra. This is the simplicity, in fact. Another class of interesting derivations is the locally nilpotent one. A derivation is locally nilpotent if for any polynomial f there is a positive integer such that by iterating n times, the derivation annulates the polynomial. Excuse me, here. This is the same that the following. If you consider the vectorial subspace generated by f, df, d squared f, etc., this is a finite dimensional space, and you restrict D to this vectorial space, then D becomes a nilpotent linear map. This is the same. Such derivations, when different from zero, non-trivial, correspond to one parameter subgroup of the polynomial group. That is the AGN. Let me explain that. More generally, if you consider a derivation of the polynomial ring, which is locally nilpotent, you have a kernel of D which is a subring of the polynomial ring, and then you may define formally an exponential series of D AC, AD, a formal series. But if A belongs to the kernel, then when you apply AD, you iterate, and D, this is the same. The operation is the same. Like that, because D is annihilated by D. And since D is locally nilpotent, this series operates in a finite form on polynomials. There is a finite sum that is applied to a polynomial. And then one may define an automorphism called exponential automorphism. And for example, if you take T, an scalar, an element of the field, then T is mapped to this exponential automorphism where you take here A as a constant, which is in the kernel of D. And you have an action of GA, the additive structure of K, there, this series. Then it is a one-parameter subgroup. In fact, one may prove that one-parameter subgroup of this type, to give a one-parameter subgroup, is the same as giving a locally nilpotent derivation. It's the same thing. And then it's a characterization, and it's for this reason that locally nilpotent derivations are interesting. Let me give some results related to the problem. Assume that n equals 2, that is, we are two variables. And then, if D is simple, it's a derivation which has no invariant, non-trivial invariant ideals, then the isotropy is trivial. That is, we have here a very rigid situation. There are no symmetries of this in this situation for these derivations. And in general, that is when D is a general and arbitrary derivation in two variables, then the isotropy is algebraic, in the sense that it's an algebraic group acting algebraically on the affine plane, if and only if D is non-locally nilpotent. That is, one may characterize, in this case, the nilpotence in terms of the algebricity, or non-algebricity, in fact, of the isotropy. Let me give an example here. In dimension 2, it's easier, obviously, but in fact, it's because a result of, I don't remember how to write that, but I will put only the result. In n equals 2, there is a characterization if and only if it's locally nilpotent, D is conjugated in the automorphic group of in the polynomial automorphic group of a derivation of the form fx la derivative with respect to y. It's a result by Chandler. And with this result, one may calculate the isotropy of this derivation, which is conjugated to the other one. And then, because it is explicit, very explicit and easy to write, then the automorphic group is defined as the following automorphisms: alpha x plus beta gamma y plus a polynomial in x. This is phi x and phi y. And with a condition, in fact, this polynomial here is not arbitrary, but verifies this. And then, as you observe this group, you see that, for example, when alpha is 1 and beta is 0 is a case, and the polynomial, there is no construction here. There is no restriction, it's every polynomial. Then the degree of the polynomial is arbitrary. This shows that, in fact, this is not an algebraic variety, because there is something there within this subset which is non-algebraic. And then it's easy to verify with this example that if the derivation is locally nilpotent, then its isotropy is not algebraic. Then the theorem there is the converse of that, in fact. The only possibility is that. Non-algebricity is equivalent to locally nilpotence. Okay? But this is no longer true in either dimension, in fact. The only part which is true is that if the derivation is locally nilpotent, then the isotropy is not an algebraic group. But there are other derivations which are locally nilpotent with a complicated isotropy, non-algebraic. There are examples. Excuse me. For n greater than 2, Dan Yang gave examples with this simple and the isotropy equal to the field, the GA, acting as translations. Acting as translation, I mean, is in this case there. It's like that. The action, for example, x1 plus a constant. Okay, it's a morpheme like that, acting in this manner, this form. Okay. She gave example like that in dimension 3 and in all dimension, different families of example with the isotropy is K. And also, she conjectured that there is no other possibility up to conjugation. Then, we are going to see that, in fact, this conjecture is not true. We will construct examples now. But before that, let me give a remark, which is important for that. Take two derivations, d and delta, in n variables, where delta is locally nilpotent and which commute with d. Then the isotropy contains the following exponential automorphism, this type of morphism. I define here the action of the morphism, of the automorphism, on the variables, on the generator of the polynomial ideal, in this form. Because d commute with delta, then commute with exponential, and then this exponential automorphism are contained in the isotropy. Okay? This is the remark. Okay? And notice also that A delta is a translation if and only if delta is linear, is a linear combination of partial derivatives, because note that the action of this in xi is xi plus delta xi plus delta square xi divided by 2 factorial, etc. And then in order to have a translation in the, for example, in the xi coordinates, then this is a constant and 0 here. Then the derivation is a partial derivative. It's more or less that. This is a constant. And then this is proportional to the derivative, the partial derivative in this variable. Okay? In general, this is the assertion. It's a remark. Then let me now give an example to show that the conjecture of Yang is in fact is not true in general. Let's start by an example in dimension 2. Consider a derivation, little delta, in 2 variables, in this, defined in this form. Delta u is 1, and delta v is 1 plus uv. This is a simple derivation. Essentially, there is an only one criterion for deciding if a derivation is simple or not, more or less, with some generalizations, which is the Chance-Sudin criterion. Which says something like that. In this case, it's like that. You have a derivation, excuse me, like that. Delta, a derivation of a ring, which is simple. D, a derivation of a ring, which is simple. Then we extend to a variable, a polynomial in one variable here, and then delta simple if and only if excuse me, it's not only that, delta is an extension of D such that delta y is a y plus b. Then delta, the extension of D is linear. We extend another variable by in a linear form. For these derivations, delta is simple if and only if D simple. Then the theorem is the simple, then delta simple. This is the criterion. And then when you have a derivation which is extended from a simple derivation in this linear form, then the new one is simple. This criterion may be generalized in several variables also by Lequesne. Lequesne gave a generalization, but also with linear things in each variable.
You have to add the fact that there is a ordinary differential equation.
Yes.
But you didn't write it. It's not any extension that will be simple.
Excuse me. You are right. It's simple if and only if. Yes. yes. Thank you. If and only if. Yes. If and only if the derivative delta R. Yes, an element here is AR plus. Yes, thank you. Thank you. Yes, yes. Thank you very much. Yes.
There is no R such that
And here is the same as D.
there is no solution of the equation.
Is wrong?
No, it's right. There is no solution of the equation.
There is no solution. Yeah. Thank you very much, Daniel. Yes. It's simple if and only if this has no solution. There is no one element in R which is solution of these differential equations here. Linear. And then we see an example. Look at this example. For example, the derivation D is the derivation R is Ku in the variable u, is the Ku, polynomials in the variable u, and the derivation D is 1 in u and is extended to the other one, and then you verify this criterion. This is not difficult to verify, that this is a simple derivation. Okay? And then one may define an extension of this derivation by adjoining any variables in the following form. The new derivation is the delta plus in the new variables is a linear combination of this form, where polynomials, the elements here belongs to this polynomial ring, okay, and in this form. This derivation, by an induction argument, one may use Sanshudin criterion and something like that, and prove that this is simple. Excuse me, this is the contrary. This is simple, and also, which is clear, D commutes with the partial derivative in the other variables, because when you apply D to x, g is V power g. Okay? Then the extension in this example, dxg is Vg, power g, okay? And then it commutes with the partial derivative in the n plus 1, in the n variables, x1, xn, okay? And then by the remark, the isotropy is Kn, acting as translation, because for every partial derivative, we have a translation. Okay? Yeah. Then we have a new conjecture, which is the following. If D is simple, then the isotropy is algebraic in dimension 3 or more, or higher, okay? Because in dimension 2, we know that this is trivial, okay? Then this is the conjecture. Let me give another remark here, and we are going to see some results in dimension 3 related to this group, which point in the direction of this conjecture. Since the isotropy is closed in AN, one may see that to be algebraic means that the degree of polynomial defining element in that subgroup is bounded. I will explain that. This is a result of Kambayashi. Here, the polynomials, the automorphism, we said that this is like that. We define that. A polynomial is defined by means of n polynomials. Excuse me, here is not. By n polynomials like that, and then the maximum degree this is said to be the degree of the automorphism. And then one may see that the subset of automorphism such that the degree is bounded. This is an algebraic variety, and in fact, this is the limit of these varieties. And Kambayashi's result says that a subgroup here within this group is algebraic when it is closed and the degree is bounded. By the isotropy, it's clearly closed because it is defined by the commutation with the derivation. And then it's closed, and then the only thing one needs to verify is the boundedness. Okay. Then now, the results I will talking about they are part of a work in progress in collaboration with Ritatore, Álvaro Ritatore, and Pierre-Louis Montagard. Assume that D is simple now, and so on. Then, there is a first theorem. If the isotropy is algebraic, then it is unipotent. That is, one may represent this group as a matrix group where the metrics are triangular and with ones in the diagonal. The neutral part of the group, because this group, the isotropy, is not in general algebraic. But there is a theory of groups which are in varieties, limit of algebraic varieties, which is more or less parallel to the classical theory, for the classical invariant theory. And then the neutral part is the subgroup, the normal subgroup containing the identity there. And then the theorem says that this algebraic group is an unipotent group, is algebraic. Okay? And also, its dimension is bounded by n plus minus 2. And theorem 3, for n greater or equal to 3, and assume that the isotropy contains a non-trivial normal subgroup which is conjugate to translations, then it is algebraic and connected. I will give an idea of the theorem 3 in a particular case, which is easier, and also where we may take off one of the hypotheses, in fact. I will give you an idea of a little more general result in dimension 3. For that, we start by a lemma, which is in the base on all these results, and it's the following. If they is simple, then the isotropy acts freely on the affine space. That is, every element which is non-trivial, is not the identity, has no fixed point. Take a point in the affine space and an automorphism which commute with D, and consider the solution of this, the formal solution of this differential equation, where we think of D as a vector field, with this condition, at t equals 0, the solution passed through P. It defines a K-algebra homomorphism. We have a solution of that. Observe that the derivation is simple, and then the vector field has no zeros. And then there is a solution, non-trivial solution here. And then x1, xn are sent to x1t, xnt, is the solution of the differential equation. Then this defines a homomorphism of K algebras such that this, excuse me? Is the differential equation x prime equal to, for example, if d, the derivative with the derivative, yes. Okay. One may think on the in the case where k is the complex number and there is a classical differential equation associated to a vector field. Okay. Yes, to t. Respect to t, exactly. Yes. Then we have a K homomorphism such that verify this condition. This condition is exactly the same that the differential equation. Here is the derivative with respect to t, exactly here. And then you replace x1, xn by x1t, xnt solution. Hence, when you, the composite of sigma and phi correspond to another solution, because verify the same condition, because phi commutes with d. Okay? Phi commute with d, then you put sigma phi in place of sigma here, verify the same equation by the commutation. Because phi belongs to the isotropy, commute with d. But it's another solution by the point Q, which is acted by phi of the point type P. Okay? The solution change the point. But then Q is the same, that is a point, a fixed point, if and only if, or implies exactly that the solution is the same because there is a unique solution of a differential equation. But since the kernel of this algebra, or this algebra homomorphism, the sigma, the kernel is stable by D because this condition. You take a polynomial on which sigma vanishes, then here is 0, and then sigma of D, this polynomial, is also 0. Okay? And then this is stable, but D is simple. Then the only possibility is the ideal is trivial. This kernel is trivial. And then phi is a one-to-one homomorphism, which implies that phi is the identity. Okay? This equation here. Then the isotropy acts freely on AN. Then now, excuse me, let me see. Okay, right. By using invariant theory, especially Further and Kraft results, there is a book where they develop the theory, or the invariant theory, for this type of groups which are invarieties. Okay? Then we proved theorem 1 and 2 using this lemma, and theorem 3 in general may be deduced from some general result of derivations, derivation and affine geometry in general, due to Derksen, Van de Essen, Fiston, and Maubach, which uses this type of actions. Actions freely actions on affine varieties. But that I will make, in fact, is, as I said, a special case of this theorem, of theorem 3. But in dimension 3, is in fact a new theorem because it's in dimension 3, and the hypothesis is a little different because it's the only thing that we assume is that the neutral part is non-trivial, because in the general result we need a normal subgroup which acts, a normal subgroup of the isotropy which acts as translations, non-trivial. The neutral part is a normal subgroup and acts, I don't know if it acts as translation, but it acts as a unipotent group. It's the theorem 2. Then the first thing to do is that observe this implies this group is in fact of translations. And this is a result by Kaliman. Then, with this hypothesis, the isotropy is trivial, is K. Then, let me recall the other theorems. We know that this is algebraic, unipotent, and of dimension lower or equal to n minus 2. This is the theorem 2. In this case of dimension 3, then, since the neutral part is non-trivial, then it is a unipotent group of dimension 1, only possibility. But by a result of Kaliman, in dimension 3, the action of a unipotent element is in fact a translation. It's in fact a translation when this element has no fixed point, which is our situation. This is a result which is true only in dimension 3. Let's conjugate to translations. Only in dimension 3. And then, using this theorem and Kaliman, we may assume that the neutral part of the isotropy is of the form. There is a translation in one variable, only that. Okay? With this simplification, now phi is a general element. Then the neutral part normalizes because it's a normal group. Then phi commute with translations. But I wrote translations in this form because it's the same thing. This is the exponential of the derivative with respect to x. It's exactly the same that the translation x plus 1 plus a. Okay? This is the same question, the same thing. For example, when you compose phi with the translation, this is the same thing that another translation by phi. Okay? For some b, which depends on a, obviously. But in this form, we may understand that clearly D commutes with the partial derivative, and then we may deduce two things. Excuse me, here. Difficult to put down. First, which is phi x? Let me write this. Now, we are in this case, three variables. And then phi x is a polynomial here. Okay, is that. But by the commutation relation, note that phi is an element of the isotropy, and then commute with D, and commute also does not commute, but verify this relation here is almost a commutation, but it's not commutation, it's a normalization. And if we stress this relation, we apply this and x, and verify that the derivative with respect to x of phi x is a constant, different from 0. And 2, phi and D restricts to the kernel. The kernel of this derivation is the polynomial ring in two variables, y and z, because phi commutes with D by definition. And then one may deduce that phi x minus alpha x is a polynomial in two variables because the derivative is a constant, is alpha, then there is this situation. And also the same calculation but with y and z, because we use derivative with respect to x, is that in fact phi the conclusion, this is a posteriori, because one deduced the same calculation shows that phi x is a polynomial in two variables, y and z, excuse me, y here, and z here is another, and phi x something in y, z, and then phi and d restrict to that. D and phi restrict to an automorphism of k, y, z, and D a derivation. But in this case, we know the situation. There are no isotropy, because if D is simple in the polynomial with three variables, when you restrict to two variables, continue to be simple. And then, by the result in dimension 2, this is the identity in this. And a posteriori, the only possibility is a translation. One may see that this part disappears, or it's a constant, in fact, and this is 1 by calculations. And finally, we get what we want, okay? The result does follow from considering this situation, this equation that is the commutation, once again, and then, excuse me, it's not finished. The commutation, and this is the result, more or less, is a sketch of the proof, in fact, okay? There are some details, maybe. But I will finish by giving some remarks or ideas or things we want to do. For example, in this case, the problem is not completely solved here in dimension 3 because we don't know if the neutral part is always trivial, non-trivial. If it is non-trivial, okay, we know the isotropy is exactly the one that Jan gave used to conjecture the general case, in fact. But there is maybe, which is that? What happens when this is trivial? Because the isotropy in general is an invariety. And then, in this case, the isotropy, the general isotropy, is a limit of varieties, but this is the neutral part, which is normal. And then, if it is non-trivial, then there is an element, and you may conjugate, and finally, we obtain a sequence of elements. Or 0 if you want. This is the identity. Another. Then, in fact, it is a problem. It's more a problem of discrete dynamic. One needs to know if this is possible, this sequence. There are a lot of examples of sequences like that for invarieties. For example, a trivial invariety is the integer number, because you may put a limit of closest subvarieties is trivial. Right? Something like that, but here it's not completely clear if it is of this form or another form, because maybe one knows that this is countable by definition, because an invariety, like the polynomial automorphic group, is a limit like that of varieties, where one is included in the other one, as closed immersion. Then this is a sequence, and we don't know if this exists. In this case, one needs to try this problem. And another problem related to this, in general, well, no, we know that this is an algebraic group, unipotent, in fact. And all elements here, then, are connected to locally nilpotent derivations. An element here is, in fact, the exponential of a locally nilpotent derivation that one may consider as an element in the Lie algebra of that. The Lie algebra associated to this group. And then the question is that if in general, when this is different from the identity, if this is a translation. Okay. Is finished? 5 minutes. Eh?
50 meters.
Ah, okay, but excuse me. It's okay. Okay, thank you very much. Excuse me.
Questions?
Ivan, if you take a Shamsuddin derivation, that is not simple. There are many that are not simple. Do you know if alt 0 is non-trivial?
If it's not simple,
Take a
and the isotropy, your question is if the isotropy is not?
Take a non-simple Shamsuddin derivation. There are many, right?
Yes. Yes. And
So consider the connected component of what you are calling alt D0.
yes.
What
I
can
don't know if this is algebraic.
You don't know.
No. In general, no. But
No, in general, we don't know, or there are examples of
if this is simple.
no non-simple.
Non-simple.
Simple.
Non-simple, I don't know.
Shamsuddin, simple, everything is trivial, right? By Danian's
yes.
result, right?
Yes. No, in general, I don't know.
Non-simple.
Non-simple, I don't know.
Okay.
Okay.
So maybe you could use if result on Shamsuddin derivation to attack this problem.
Okay.
Does anyone have a question?
So I have two questions. The first is, why restricted to polynomial rings?
The what?
Why restrict to polynomial rings?
What? Street?
You study only derivations on polynomial rings.
Yes.
Why?
Okay. No, because I am interested in the group of automorphisms, affine automorphisms, the so-called affine Cremona group, and then it's natural to consider this type of situation there. But in general, one may do the same questions for a K-algebra.
And do you also have similar results or a conjectural structure theorem for foliations, one-dimensional foliations instead of derivations?
No. In some cases, in dimension 2 and things like that, yes, the symmetries is finite, for example, for a simple a foliation coming from a simple derivation, for example. But in general, no. In general.
Thank you.
Okay. Does anyone has a question?
Similar to what Jorge asked, did you study Artinian algebras?
No.
Because it seems to be more easy, and maybe
Yes.
there is. Okay. Well.
No, I don't know. In general, we work only with this at the moment,
Okay.
with polynomial algebras.
Thank you.
Your result with Gustavo Mendes was only for polynomials or any
Polynomials. Polynomials.
So what was the connection with the important group?
Excuse me? No,
What was the connection with the important group that you mentioned at the end?
The connection is that the neutral part is a unipotent group.
Because there is a versal
In fact,
by the shuffle problem.
yes, I don't know, but in general, for the invariant theory for these invarieties, groups which are invarieties, there is a Chevalley-Jordan theorem, and then one may use this decomposition to verify that the semi-simple part is trivial and then is unipotent is this in general the idea, but I don't know if this answered your question.
No, I was just wondering, so you have this sort of important group and anything that is whatever ends then important, because I mean it's the same thing that important the algebras is a quotient of this algebraic group. So I was wondering if somehow this versal object will shed some light on the type of the important the algebra that you encounter.
Yes, I don't know.
Okay, more questions? No? Okay, so we thank you again.
Thank you.
Thank you very much.